Just hit it once, yeah. There you go.
Yeah. Alright, I'm gonna start. Alright. Okay, so they give this problem, it's a beam, it's a T-beam if you want to call it that, an upside down T, and it's being bent. They give you the moment as 100 times an inch, and this is a cross section right here. Alright, so since it's not a standard shape, you have to find the centroid, or the neutral axis. So you're going to have to break this up into shapes you know. Alright, so you can break this up into two rectangles, right? So you break this up into two rectangles. Alright, and you can define the x-axis underneath this shape. Alright, and you want to find the neutral axis. So you want to find where the neutral axis is on this upside down T. Okay, so I'll call this shape 1 and shape 2. Alright, do you guys remember how to find the centroid? You have y bar times the total area is equal to the sum of the individual y bars times the individual areas. Alright, so there's two shapes. So we're gonna have to solve for the neutral axis, which is this y bar. Okay? So we have y bar is equal to y1a1 plus y2a2 over the total area, which is just a1 plus a2. Alright, so I define the x-axis from the bottom here. So we want to find where y bar is with respect to this. So we want to find the distance from here to here, wherever it is. It's going to end up over here, but alright, that's the y bar. Okay, so you have to find y bar 1. What is y bar 1? It's just half this distance, right? This is y bar 1 over here. Y bar 1, and what about y bar 2? See here. It's this distance plus half this distance, right? Okay, so this distance is 1 inch, this is 3 inches, so this distance from here to here is 2 inches, right? Okay, so so what is this y bar 2? I'll ask you guys. 2. It's 2, yeah. Half of 2 is 2 plus 1, so it's 2, yeah. So this is equal to 2, this y bar 2, and y bar 1 is equal to what? 1 half, exactly. 0.5 inches, okay. Alright, so you could just substitute it back into this. This is equal to 0.5 inches multiplied by the by the area. It's 1 inch multiplied by 4 inches plus y bar 2 is 2 inches multiplied by 1 inch times 2 inches, all divided by 4 inches times 1 inch plus 2 inches multiplied by 1 inch. Okay? So you get the y bar you get is it's 1 inch. Okay, so the y bar you get is 1 inch. So the neutral axis is right over here. I'll redraw it. Alright, so you got this shape. Alright, so this is a neutral axis. And why is this important? What's the stress at the neutral axis? 0, exactly. Okay, so that's important to know. Alright, so we found the neutral axis. Now we want to find the stress. We want to find the maximum stress, right? So there's going to be a stress. This beam is being, there's a moment to this beam. So this bottom face is going to be in compression, and the top face is going to be in tension. Okay, so we want to find where the stress is max. So we're going to have two stresses from this, right? You see, you're going to have one from compression, one from tension, one from compression. So let's get those. So first we'll find the stress and tension. So that's equal to my over I. So we also have to find the moment of inertia first. So let's do that, because it's going to take up most of the board. Can I erase this now? Good. Alright, so we found the centroid or the neutral axis. Now we want to find the moment of inertia. Alright, so let's find, we have to find I1 and I2. Alright, and then we have to get the total moment of inertia, which is just going to be the sum of both of them. So what's I1? I1 is 112 B1H1Q plus A1D1 squared, right? And you know this, okay? You might know the formula, but you have to know what these are. Okay, so I1 is equal to 112. B in this case is what? I'll ask you guys. 4, exactly. 4, and what's H? Exactly. A lot of people forget how to do moment of inertia for some reason. Alright, so the area of this cross section is 1 times 4. And these, all the units are inches, so I'm just leaving it out. And what's the distance D in this case? What? 0.5, yeah. Half. Okay, 0.5 squared. Alright, so the moment of inertia for 1 is equal to 1.33 inches to the 4th. Units are important, it's inches to the 4th, right? Because you have inches times inches cubed, that's inches to the 4th. Alright, so I2 is equal to 112 times, what's B in this case? 1, exactly. What's H? 2 cubed plus, the area is 1 times 2. And then the distance is what? It's 1, yeah. 1 squared. Alright. So the moment of inertia you get for this is 2.67 inches to the 4th. Alright? So now you can get the total moment of inertia. The total moment of inertia is I1 plus I2. So I total is equal to I1 plus I2, which is equal to this added to each other. So the total you get is 4.0 inches to the 4th, okay? Alright, so now that we have the total moment of inertia, we're going to know what is the distance for y in tension. What's the y distance we need? It's measured from the neutral axis. If we want sigma t, which is the stress in tension. What's the y value? 2, exactly. This is a neutral axis, it's just 2. Okay. Alright, so sigma t is equal to, the moment is just 100, it's given in the problem, 100 pounds times an inch, multiplied by y, which is 2 inches, all over the total moment of inertia, which is 4.0 inches to the 4th. Okay, so sigma t is equal to 50 psi. And okay, they're asking for the maximum stress, but we don't know if this is maximum yet. Let's find the compressional stress. So I'm going to erase this. Alright, so now sigma, I'll call it C for compression. It's also my over I. Remember, this is the total moment of inertia. So this is 100 pounds times an inch multiplied by y. The distance y in this case now is what? 1, exactly. 1 inch over the total moment of inertia, which is 4.0 inches to the 4th. Alright, so, and remember, this is compression, so it's minus. I almost forgot the negative sign. Okay, so this is minus 25 psi. Sorry for the squeakiness. All right. So they ask you to find the maximum stress. So it's obviously the stress and tension. Okay, so to get the neutral axis, what you have to do is you have to set a reference point. I usually take the bottom. You can take the top. It doesn't matter. You have to find y bar, the centroid. The centroid is going to be the neutral axis. So you have to do you have to break this up into 2 figures, 2 rectangles, and then you could find y bar. All right, you can watch a video to see what I did, and you'll be able to get it. I want to get through all the problems. Any other questions? This problem I took out of the textbook. The other problem I should credit Gupta because that was from his exam. I stole that from his exam, so I never asked him if I could use it, but hopefully he'll be okay with it. Okay, all right, so this is the next problem. I'm going to do the diameters first. Okay, all right, so now we know everything in this problem, right? They want to know what's the reaction at A and C, and they want to also know the normal stress in each portion of the rod, okay? So first we have to find the reactions at A and C, and then we will have to find out what's happening with this rod, and the stress in this rod, and the stress in this rod, right? So what's the first step? If you're taking the exam, I would draw a free body diagram first of this thing, right?
Real quick, what are those distances?
What?
Those just lengths.
Oh, okay. LAB is 25, so this is 25 inches from here to here. Sorry. And then from here to here is 15 inches. Okay, so free body diagram. All right. So you got 6 kips over here, 6 kips over here. And then, okay, all right, so what reaction do you expect here? Is it going to be up or down? It's going to be up, exactly. So this is RC. What about here? Is it going to be up or down? No, it's up. Yeah. It's okay. RA, okay. Because you could think of this rod's going to be in tension, right? It's going to be pulled. So this is going to be in compression. So this has to be up, okay? So that's a good way of remembering it, okay, when you draw the free body diagram. All right, so let's sum the forces. You're going to notice this is statically indeterminate. So if we sum the forces in the y direction, what do we get? We got RC plus RA is equal to 12. And this is kips. Okay. All right, so it's statically indeterminate. You can't do anything else with statics. You can't sum the moments or anything. It's not going to give you anything. All right. So now we have to use mechanics of materials. Well, we know the deformation. We know the deformation of this rod that it is going to be experienced is going to be equal to this rod, right? Let me draw another free body diagram to show you what these rods look like. Here's a second free body diagram. I'm going to cut it over here. So this is this force is RA. This force is RA. Okay, and let me draw BC. Right? So you got this force. We determined RC, but I'm not going to call it RC yet. Okay, so this force over here has to be equal and opposite to the one that this produces on this block, or this rod, sorry. So this is RA, right? And we have this force going down. This is 6 kips. This is 6 kips. All right, so what is this? What is this on the bottom? It's RC, but what is that? This is 12 minus RA, right? You guys see that? Alright, so this is the individual free body diagrams. This is rod AB and this is rod BC. Okay? Alright, so from mechanics of materials, we know that delta AB has to equal delta BC, right? So we know delta AB is RA, right? This is the only force acting on rod AB. So it's RA times LAB over EL over AAB times the Young's modulus. Oh, I didn't give you the Young's modulus. Okay, the Young's modulus is 0.45 times 10 to the 6 psi. Okay. All right. So the Young's this is all the same material, by the way. This material is the same as this material. All right. So there's one Young's modulus. I'll just call it E. So this is equal to 12 minus RA, right? That's a force, and LBC over ABC times E. All right, so E is the same throughout the material, so they're going to cancel. If you move this over here, they cancel. All right, so you get RA times LAB over AAB is equal to 12 RA. This is just algebra multiplied by LBC over ABC, right? Because the Young's modulus cancel. And I'm going to erase this now. This part of the board. All right. Okay. All right. So we're over here right now. What we want to do is move RA to the left side. Okay. So you have RA multiplied by LAB over AAB, and then you're moving that to the other side. So you have plus LBC over ABC is equal to 12 times LBC over ABC. All right, so you could just move this over here to the other side. So you get RA is equal to 12 LBC over ABC divided by this whole thing, LAB over AAB plus LBC over ABC. This is just algebra. You guys could all do this. All right, so if we want this to look nicer, we can multiply the top and bottom by the areas. So now what I'm going to do is just do a little manipulation to get this cleaner. So you can multiply the top and the bottom by this. BC times AB divided by, so I'm just multiplying by 1, it's the same thing. ABC, AB, right? That doesn't change anything. Okay, so you get RA, so I'm coming up here from over here. So you get RA is equal to, these are going to cancel, this one and this one's going to cancel, so what do you get on top? You get 12 AB times LBC divided by, and this one is going to cancel, this one's going to cancel this one, and this one's going to cancel that one. So you have, what do you have? You have ABC times LAB plus AAB times LBC. Okay? Alright, so that's a little more simplified. So now you could just stick in each number. You could get the area, the cross-sectional area of AB, and that's equal to pi over 4 times the diameter AB squared. All right, it was given in the problem. I'll just list those values out. ABC is equal to pi over 4 times DBC squared. All right, so you can get these values. I'll just give them to you. They give you the diameters of both of the rods. All right, so for AB, it's 1.23 inches squared, and then for BC, it's 3.14 inches squared. And they give you the lengths as 15 and 25 inches. Okay, so LBC is 15, LAB is 25. All right, so the reaction you get, so RA, after substituting everything into here, RA is equal to 2.28 kips. This is 2.28 kips. All right, so that's one reaction. And then the other reaction, you could go back to the statics. You had RA plus RC is equal to 12, right? So then you could get RC is equal to 12 minus 2.28, and you get 9.72 kips. Okay, so they're asking, first they were asking for the reaction forces, and now they want the stress in each rod. Okay, so once you find the reaction forces, then you can get the stress of each rod. Remember, the top rod, AB, is in tension, and the bottom rod is in compression, BC. So we know the stress of AB. Remember, this is in tension, so it's the force over the area, so it's RA over the cross-sectional area, RAB. So that's equal to, I'll just give you the value. You just stick this 2.28 kips over here, and the cross-sectional area is this value, 1.23 inches squared. So you get 1.85 KSI. Okay, so this is the stress for AB. And then they ask for the stress of BC. Remember, this rod's in compression. So all it is just RC over A, BC. It's minus RC over A, BC. So this is just 9.27 kips over the cross-sectional area, which is 3.14 inches squared. So the stress you get is minus 3.10 KSI. Any questions? So this is a stress in rod BC, this is a stress in rod AB.
How come we were able to say the deformation was the same in both parts again?
Okay, so right, you have these two walls, right? You have this wall, you have the rod, the two rods, and there's another wall. All right, these walls are rigid, right? So you have, from mechanics, you have the sum of delta is equal to 0, right? Because the total deformation has to be 0 because it's in between two rigid walls. So the net has to be 0. This thing can't deform. It can't deform. Like, yeah, this rod's going to deform and this rod's going to deform, but the deformation has to be equal to each other, right? Because this is gonna extend and this is gonna shrink, right? So we have delta AB. It's gonna expand, so it's positive. Minus, this is gonna shrink, so it's delta BC is equal to 0. Now you see? You could just say the deformation of this one is going to equal this one, in that case. No, but this is like a more formal, like you understand what you're doing. Okay. Any other questions?
Does that also have to go with them being the same material too?
No, it doesn't matter.
Alright.
If you had different materials, they still would be equal to each other. Look, if you move this over and it's different material, it's the same thing. Okay. Good job. Still recording? Yeah. Okay. And remember, I picked these problems for a reason. They're good reasons. So, I mean, take what I'm saying. Okay, so you got this bolt over here. They give you the diameter. This diameter, I'll just call it D. It's 2.5 inches. All right, so I'll list what they give you. So given, they give you the Young's modulus. The material's steel, so it's 29 times 10 to the 6 psi. You don't have to remember Young's modulus. On the exam, he's going to give you, if he says it's steel, he's going to give you the Young's modulus. All right, but that's like a common value you're going to see throughout this course. So, oh yeah, and the Poisson ratio is 0.3. Okay, all right, and they say the diameter is observed to decrease by, okay, so D is going to decrease by 0.5 times 10 to the negative 3 inches. Okay, and they want to determine the internal force of the bolt. Okay, all right. So if you think about this, the diameter is gonna be decreasing. Why? Because like when you tighten this bolt, is this bolt in compression or tension?
Tension.
It's in tension, right? Okay. Bolts are always going to be in tension. All right. So if you draw a free body diagram of the bolt, I'll draw it here. All right, this is a bolt. All right, and I'll just call this force P. This is what they're asking for. They want to know this force over here, P, right? Okay, but they give you stuff you need. Obviously, they're always going to give you, whatever they give you in the problem, you need it. And if you use these, if you use everything they give you, you're going to obviously solve the problem. They're never going to, they can give you something you don't need, but they're never not going to give you the information you need to solve the problem. So, all right, so let's think about it. What do we have, right? We're obviously going to have to use Hooke's law. They give you the Poisson ratio. That's a dead key. That you have to use Hooke's law. So just think about it like this is how I solve problems. Like seriously, oh, what are they giving me? Oh, they're giving me the Poisson ratio. I need Hooke's law. They're giving me the Young's modulus. I'm going to have to find maybe a stress or whatever. All right, and they give you this diameter that is shrinking. So that they give you delta, right? So this is going to be delta for the diameter. So you know what? Let me make this easy for you. I'll draw an x direction to be this way, y direction to be this way. So this is x, y, and z is outward. It's out of the board. All right. So okay. Yeah. All right. So they give you So they give you this diameter. They say it's going to shrink. It's going to decrease by 0.5 times 10 to the negative 3. So this is actually, it's either delta z or delta y. I'll just call it y because they give the diameter in the y direction. So delta y is equal to minus, it's shrinking, 0.5 times 10 to the negative 3 inches. Okay, so they give you this, right? All right, so we're going to have to use Hooke's law. So let's use Hooke's law because they give you the Poisson ratio. So Hooke's law, right? This is my thought process. All right, so you have epsilon x is equal to sigma x over E minus the Poisson ratio sigma y over E. I'm just going to list out each one. Minus the Poisson ratio sigma z over E. Epsilon y is equal to sigma y over E minus the Poisson ratio of sigma x over E minus the Poisson ratio of sigma z over E. All right, and then epsilon z is equal to sigma z over E minus the Poisson ratio of sigma y over E. All right, you guys follow. I'm just hooking up. I'm just plugging in Hooke's law, right? Okay. All right. So this is Hooke's law. right, for epsilon x, y, and z. But what do you know about this? I told you this is the x direction, right? So there's only a force in the x direction. So what's sigma y and sigma z? Zero, exactly. So just get rid of that. Just be like, peace, I'll see you later. Oh. Alright, so this is 0. Sigma y is 0 and sigma z is 0. See you later. Okay, this is 0, this is 0, this is 0, and this is 0. Alright, so now you know epsilon x is sigma x over e. You know epsilon y is minus, maybe I should rewrite it because it's going to be hard to see. I'll rewrite it. Because I got one more problem and I got enough time. Alright. Alright, so epsilon x in that case is sigma x over e. Alright, epsilon y is equal to epsilon z, they're equivalent, is equal to minus mu epsilon x over e. You guys agree? They're equivalent. They're the same. What's this? Okay. Okay, so now you got the strains in all the directions, but we only need this, right? What is this? What is epsilon y? Epsilon y is equal to delta y over the original length, which is d. Do you guys see that? That's important. Alright, so the change in diameter over the original length of the diameter. So they said in the problem that it's going to change by 0.5 times 10 to the negative 3 inches. So I told you that was delta y. Okay? So this is equal to this, while this is equal to this, and we're going to have to find p, right? What do we know about sigma x? Sigma x is equal to p over a. Wow. All right. So, okay. All right. So what's a in this case? It's pi over 4 times d squared. All right. So we're looking for this, right? So how are we going to relate that p with all the equations we have? Well, we know sigma x is p over a. You can stick this over here, and you know this quantity over here is equal to this. Well, you know this, 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 and you want to find this. So, okay. So let's just equate things so we can see what I'm talking about. You guys see where I'm going with this, right? Yeah. Okay. I think this is competency right here. This question, something similar, very similar to this. Okay. All right. So we got the strain in the y direction is minus mu sigma x over e, and that's equal to delta y over d, right? We need to find this. Once we find this, we can find the force, right? Or we could just directly substitute this into here. So you have minus mu p over ae is equal to delta y over d. Remember, this delta is negative because they said it's decreasing. So a minus and a minus, they're going to cancel. But I'll leave it in for now. So you have p is equal to ae delta y, this is minus, over mu, right? D. There's a d here, right? So I move this over here. I divided this, and this is over here. So I solve for p, right? This is equation for p. Well, we know this, we know this, we know this, we know this, we know that. So you get the answer. All right. So I don't have a is equal to pi over 4d squared. All right. D squared is 2.5. So you could just solve for the area. And we know this is 0.3. This was 2.5. And this you could just solve for. E they gave you in the problem. And this delta y is negative because it's decreasing. So this is minus. I should have put a minus there. Or you could just leave it positive and just say it's minus 0.5. Right? Okay, not to get confused. Times 10 to the negative 3. All right, so the force you get after you plug in the values you get P is equal to okay, I'll just write it out. Pi over 4, it's minus pi over 4 times 2.5 inches squared times minus 2 times 10 to the negative 4 multiplied by 29 times 10 to the 6 psi over 0.3. Okay? And what is this value? What is that? This is a strain. This is just epsilon y. Because you know this is epsilon y. So you could just leave it as epsilon y if you want. So it's AE epsilon y over the Poisson ratio. Or you could just substitute every value in that I gave you. You guys follow? Okay. Okay. Oh, I should give you the value of the force. All right. So the force is 94.4 kips. All right. So I got one more problem. Any questions? Ask me now or forever hold your peace. All right. That's competency right there. I'm not saying this is the exact problem, but it's probably really similar. You know. This is Gupta's exam problem too. Oops, this should be. Okay, so they give you this. This is A, B, and this is C. So they give you this distance from here to here, and this distance from here to here. It's 0.5 meters. 0.5 meters. They give you a torque at the end. So this is T. I'll just call this T, which is 50 Newton meters, okay? And they give you the material properties of each rod. They give you the shear modulus, so I'll just write it down. Rod AB. This is what they give you about rod AB. They give you G is equal to 50 GPa. They give you the radius. It's the radius of AB. Obviously, these are two different materials, but they're the same radius. So RAB is equal to 2 centimeters, and they give you the length is obviously 0.5. So AB is equal to 0.5 meters. And then let me give you the information about rod BC. Okay. So they give you the shear modulus is 25 GPa. RBC is obviously the same as 2 centimeters, and the length they give you is the same. This is BC, this is 0.5 meters. Okay, so we got everything. He asked you to find the maximum shear stress for part A. So we have to find the maximum shear stress. Once we find the maximum shear stress, then they're going to also ask us to find the angle of twist at B and C. So we're going to have to find the angle of twist over here, on this surface, on this face, and the angle of twist on this face, okay? Alright, so, let me ask you guys, very simple problem. Okay, so, what is the maximum shear stress? Let's start with that, because that's what they're asking for first, right? If you cut this anywhere, in this free body diagram, if you cut it here, 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 it doesn't matter where you cut it, it's in equilibrium, so the torque is always going to be what? 50 Newton meters, exactly, no matter where you cut it. Okay, so remember, it's all these problems they're static, nothing's moving. So, all right, so we have TR over J. right? And J is equal to pi over 4. Remember, this is one complete rod. The radius is the same for both sections. So I'll just call that R, okay? So tau max is equal to TR over pi, sorry, this is pi over 2. Whoops. And this is R to the 4th. Pi over 2 times R to the 4th. Okay, so this is equal to 2t over pi r cubed, right? So we know t is 50. We know r is 2 centimeters, so we can get tau max is equal to 3.98 MPa. So this 50 Newton meters, and this is 2 centimeters, so it's 0.02 meters, right? Okay. All right. So this is the maximum stress. So they asked for the maximum shear stress, and then the second part of the problem, they want to know the angle of twist at B and C. Okay. So I'm going to erase this now. All right. So what's the angle of twist at B? What is it? What's the formula? It's TL over JG. I just drew a G. It's JG. Okay. All right. So this is rod AB, right? The length is AB, but they're the same. The torque is always, it's throughout this whole rod, it's going to be 50. So this is 50 Newton meters, right? And J, maybe I should give you the value of J. That would be a smart idea. Okay, so J is equal to, did I determine J? Yeah. J is equal to 2.513 times 10 to the negative 7 meters to the 4th, right? Okay, so we need this value J. So J is the same throughout the rod, so we know J now. So that's known. This is 2.513 times 10 to the negative 7 meters to the 4th, right? And GAB was given. What was that? That was 50 GPa. Okay. So we know everything. So we can get the angle of twist at B. So the angle of twist at B is 0.00199 radians. All right. So we want the angle of twist in terms of degrees. So what do you have to do to this? Multiply by what? The reciprocal. Yeah. 180 over pi. We want to get this in degrees, right? If you wanted to get into radians, if they gave you degrees, then you multiply by pi over 180, but you want to get this into degrees, so it's the reciprocal of what you said. So yeah, it's 180 over pi. So this is 0.114 degrees. This is a 4. Okay. Okay. All right, so that's the angle of twist at B. And now we want to know the angle of twist at C. Well, the angle of twist at C has to be the angle of twist at B plus, let me write it. Okay. So we found the angle of twist at B. So we want to know the angle of twist at C. So it's this, you have this line over here, right? All the way to here, and then there's some angle over here, whatever. So it's going to be the angle of twist from this face and the angle of twist from this face. So theta C is equal to theta B plus T, which is the same. The torque throughout this whole thing is the same. TLBC over TL over JGBC. Okay? Remember. And then you're going to get rads over here. So this is going to give you rad. So you have to multiply this by pi. 180 over pi. Okay? So what I was saying, this is going to give you radians. So you have to convert into degrees since we have this in terms of degrees. Or what you could just do is leave it in terms of radians and then at the end convert it into degrees. Okay? So the angle twist at C is this value. I'm leaving it in terms of degrees. It's 0.114 degrees plus, I'll just substitute the values in because I have time. 50 Newton meters multiplied by 0.5 meters all over. J was 2.513 times 10 to the negative 7 meters to the fourth. And the shear modulus was what? What was it? 25. 25 times 10 to the 9 PA. Okay? So, and this is multiplied by 180 over pi. Because I'm converting this, right now it's in radians. I want to convert that into degrees. So we get the angle twist at C after you plug and chug. You get 0.342 degrees. And that's it for the review session. So, that's it. Yeah, I'll stop. I got it.